The transition metals are the largest group of elements in the periodic table. They are generally known for their hardness and their high densities, melting and boiling points. The group includes the 38 elements from scandium to zinc, yttrium to cadmium, hafnium to mercury, and rutherfordium to niobium. The transition metals also include the 30 elements that make up the lanthanide and actinide series, but these elements are traditionally considered as separate subgroups. The most well-known transition metals are copper, silver, and gold. People have used these metals to make coins and jewelry for thousands of years. But many other transition metals are also important to society. The elements iron, nickel, and titanium are used in technology production, and many can be combined to create metal alloys that are vital for modern construction, commerce, and industry. The transition metals in general are hard, dense, and shiny. They have high melting and boiling points, and they are good conductors of heat and electricity. As with all metals, most are malleable and ductile, meaning they can be flattened into sheets or pulled into long wires without breaking. Transition metals share many traits, but the properties of individual transition metals can differ from one element to the next. For instance, only copper, silver, and gold are usually found in their pure metallic states. All other transition metals interact with oxygen in the atmosphere, so they're usually found only as compounds. The transition metals iron, cobalt, and nickel are the only 3 elements known to produce a magnetic field. These differences in chemical and physical properties may be better understood by taking a closer look at the periodic table. On the periodic table, the elements are listed in order of their atomic number. The atomic number represents the number of protons in an element's nucleus. In its normal or ground state, this nucleus is also surrounded by an equal number of electrons. As you read the periodic table from top to bottom, each horizontal line is called a period. Each period represents the number of electron shells the element's atoms normally have. For example, 4 electron shells are in an atom of titanium, so it lies in period 4. And an atom of hafnium in period 6 has 6 electron shells. The transition metals in period 7 are called transactinides because they come after the actinide series. All these elements are radioactive, and they can be produced only under unnatural conditions, such as inside nuclear reactors or high-energy particle accelerators. They are very short-lived. Some last for only seconds. As a result, scientists know little about these elements. As you read across the table from left to right, the vertical lines of elements are called groups. Elements in one group generally have the same number of electrons in their outermost electron shells. These electrons are called valence electrons. It takes 8 valence electrons to fill an outermost electron shell and make an atom stable. For most groups on the periodic table, the number of valence electrons an element has corresponds to its position on the table. For instance, hydrogen in group 1 has 1 valence electron, so it's very interactive. Beryllium in group 2 has 2 valence electrons and it's slightly less reactive. Boron in group 3 has 3 valence electrons, and so on. But the transition metals do not follow this pattern. These metals have valence electrons in 2 shells instead of just 1. Like other elements, the transition metals have electrons in their outermost shell. But they also have valence electrons inside this outermost shell, in an interior shell called a d orbital. The d orbitals hold between 1 and 10 additional valence electrons. When transition metals react with other elements, these partially filled d orbital electrons determine how the elements interact.